So in this video, we will understand the concept of moment of inertia. Now this moment of inertia is very similar to mass. So just like about when we have, when any object has mass, right, which we usually denote by m. So in a translation motion, we know that the momentum is mass times velocity. The net force which acts on the body is equal to mass times acceleration. You know all that. So there is a term called mass, and we have been very familiar to it. When we analyze rotational motion, uh, we this moment of inertia is a term which is equivalent to mass in translation motion. So let's see how and what is that term. So we have been arguing that, and again by the same argument we start, that this is the rigid body which is the door, and this is composed of many billions and trillions of particles. So the net torque which acts on the body will be equal to the sum of the torque on each of these particles, right? And what will be the sum of the torque of each of these particles? So let's say this is the ith particle. So the torque on the ith particle will be r vector, this r vector cross the force which acts on this ith particle. What is the force which acts on the ith particle? That will be the mass times acceleration of the ith particle. And we know that in rotational motion, each particle moves in a circular motion. So this particle will have a circular motion, right? So the net torque on the entire door will be what? Summation of all the torques on each of these particles, which will be ri vector cross mi vector into ai vector, right? Now, since that this ith particle, each particle moves in a circular motion. So what is the acceleration when an object or any particle moves in a circular motion? So we know that when an object moves in a circular motion, its acceleration is given by this term, which is omega square r. In fact, it is minus omega square r er cap. This is the centripetal acceleration, and plus the tangential acceleration, which is ri cross into alpha. So this is er cap, the radial direction, and this is et cap, the tangential direction. So this we have seen, right? We know that in a circular motion, this is what is the acceleration. Now when we expand this term and do the cross product, so what do we get? The first term is ri vector cross minus m omega square r er vector. So er vector is nothing but the direction in the radial direction, and ri vector is also a vector in the radial direction, right? Because this particle is moving in a circular path. So this is the ri vector, and this is in fact the er cap direction. So both, given that both the vectors are in the same direction, so they will cancel each other for cross product. So this will become 0. And what is so the radial component will become 0. What we will get? So what we will have is only the tangential component. So the tangential direction is this one. The tangential direction is 90 degree perpendicular to the radial direction. So ri vector is radial direction cross this term is ri alpha into et cap. So given that this angle is 90 degree, so you will get m ri into ri square alpha, right? And et cap, let's call it et cap. So that's the tangential direction of this ith particle, right? So this is the vector, but the magnitude is this mi ri square alpha, where alpha is the angular acceleration of this ith particle. And we know that each particle will have the same angular acceleration. So in the rotational motion, even this particle will have a circular motion, and this particle will also have the same angular acceleration. This particle will also have the same angular acceleration, right? So this we have seen this, we know that, right? Because each particle, because in the same duration, like if this door completes one circle, then each particle will complete one circle at the same time, right? So this is the property of rigid body which we have seen, right? So the angular acceleration of each particle is the same. The velocity will be different, not the angular velocity, the linear velocity. The angular velocity also of each particle will be same, but the linear velocity, right, that will be different. So this particle which is near to the hinge will have a smaller linear velocity. This particle which is away from the hinge will have a higher linear velocity. Why? Because in the same time interval, this particle covers a larger distance, this particle covers a smaller distance, but the angular displacement of both, these two particles are same, because in that same time interval they cover the same angular distance, right? So if this door moves from here to here, the angle which this particle traverses will be the same as the angle which this particle traverses, right? So the angular displacement will be same. So that's why the angular acceleration also of each of these particles will be same. So this angular acceleration can be taken out, right? And then this can be clubbed together. Now you see this torque is now, we can write this as torque is equal to, we can call this term as I and alpha. So we can say that torque is equal to I alpha, where I is where we define I as moment of inertia and alpha is angular acceleration. Now this is very similar to the link translational motion force, right? Where we define force vector is equal to mass times acceleration vector, right? So here also where A is acceleration and m is the mass. So now in rotational motion, this is the torque. Now this is equal to this term I times angular acceleration. So this is acceleration. This is a term called I. So we call this term as moment of inertia. We call this term as moment of inertia, and this term is very similar to mass in rotational motion, right? So that's conceptually what is moment of inertia. In the next video, we will try to calculate this moment of inertia for some bodies. So this how to apply this will become more clear.